Hello, just somebody tell me when I should start.
Okay. Hey, Wolfgang.
Hi.
Give us a couple of minutes. I think here it's considered a bad taste to start on time. What is this idiot doing? Somehow it has very hard time starting. I just put it on mute.
Oh.
Hello? Yeah, okay. Sorry, Wolfgang. So let's start. So everyone, hello, back to the afternoon session. And we start, and I'm happy to announce our first speaker, who is Wolfgang Lerche, who will have to tell about his own subject title.
Yes, sorry, I didn't tell the title. But anyway, let me thank you for inviting me. Unfortunately, I can't come in person. Actually, I realized only yesterday that it's half an hour and 1 hour, not 1 hour. So I had to cut down the talk, and I hope still it will be understandable. So let me share the screen. Let's see how this works. Which one do we take? This one, maybe. Does this work? Do you see the mouse? Can this be seen, the screen, and can the mouse be seen?
Yeah, everything is seen. So
very good.
You are not in full screen mode, but other than that, all is good.
Yeah, I prefer to see the upcoming slides here on the side. So, I will talk about work done in collaboration with Sujong Lee, Guli Lockhart, and Timo Weigand last year at CERN. And it's a topic which is centered in the circle of various other topics, quite different ones actually: weak gravity conjectures, F-theory, geometry, Holomorphic theory on fourfolds, and modular anomalies and Jacobi forms. So here some little motivation. At least this was a history, and later, as so often, the subject developed in its own right, while losing the original motivation out of sight of it. Yeah. So the original motivation is that is a matter of observation that often subtle consistency conditions like weak gravity conjectures, such as decay properties of black holes and so on, are often guaranteed by mathematical properties of some manifolds or some modular functions and so on. Yeah. So there's an intrinsic relationship between this kind of subtle consistency conditions and mathematical properties. So for example, we have this well-known dogma that there shouldn't be any global symmetries in quantum gravity. And if you follow this rule, that maps into the degeneration geometry of a Calabi-Yau manifolds at large complex structures or large sizes. And so at these infinite distances, we will have asymptotically massless towers, either Kaluza-Klein modes, which corresponds to decomplexity, or tangential strings with various properties. And these things must be consistent. So there's also a built-in consistency condition. And on top of this, for example, unrelated, if you have a string spectrum, for example, another theory which has gravity, with enough supersymmetries, then there should be super extremal states in the spectrum such that black holes, extremal black holes can decay and don't form massive remnants, for example. And this can be traced back to modular properties of Jacobi forms, which appear in the elliptic genera. And so this is what we follow a little bit. We start from the geometry, actually F-theory geometry, get to tangential strings, solitonic strings, and in the end, we will find exactly the required properties. However, in 4 dimensions with n equal 1 supersymmetry. So this is a new feature here. So this is the overview of the talk. So I review tangential emergent strings from geometry, which is well-known stuff, and this is mostly in 6 dimensions. And I will point out how the geometry leads to the computation of non-perturbative elliptic genera, which are characterized by various properties, and in particular display holomorphic anomalies. Then we go to 4 dimensions, which is the main topic. Here, the new ingredient in F-theory is that we need 4 fluxes on 4 folds, which quite crucially influence all these considerations of elliptic genera. And then we go through some surprises, some unexpected non-modularity or quasi-modularity properties, and then in the end we come back to the tests of the weak gravity conjecture. So very briefly, we consider solitonic strings in F-theory. F-theory, just to remind you, is just a non-perturbative 7-brane geometry in type 2B strings, and we have compactifications of this fictitious 12-dimensional theory on some Calabi-Yau K-folds, which are complex K-dimensional. They are given by base spaces fibered by elliptic curves. This encodes the coupling constant of the type 2B string. And these elliptic curves can degenerate in certain ways when we are here in the base of a certain singular loci. And in particular, we can ask what happens to this ribbon wrapping around a curve C0 in the base here. What happens if we go in the modular space to a location where this shrinks to 0 size? And then, of course, just from dimension counting, we expect a tangential string appearing. In the 6th dimension, this is very well investigated. And the main classification comes from the self-intersection properties of this curve. If it's negative, then these cycles can be shrunk only at finite distance in the modular space, which corresponds to strongly coupled non-critical strings, E strings without gravity. And otherwise, they can be shrunk only at infinite distance. It's the boundary of the modular space. This is where we're interested in. In particular, if the self-intersection is 0, then we get solitonic heterotic strings. So what can we say about those? Well, the robust quantity to look at is, of course, the elliptic genus, which is a partition function in the Ramon-Ramon sector. Here we assume a 2-dimensional world sheet for simplicity. 0-2 sigma model, and we introduce also a U1 charge in the game. And it's important because later we want to go to 4 dimensions, and the elliptic genus in 4 dimensions vanishes if we don't have a U1. So that's why we start with a U1 here at the beginning, and it's not related to an R symmetry. It's just a left-moving arbitrary U1 gauge symmetry in the theory. So we have a generic expansion of the elliptic genus, more or less by definition. And the coefficients are degeneracies, which are labeled by the excitation level of the string and U1 charge. So we have this kind of expansion. and it is expected to have definite modular properties under modular transformations of the worldsheet. In particular, it has a modular weight of 1 minus d halves when we are in d dimensions. So it's -1 in 4 dimensions and -2 in 6 dimensions. Now, why don't I start with this? Why do I go via F theory? The point is that actually one has non-perturbative extensions of this, which don't have a worldsheet description, or at least a weakly coupled worldsheet description. And one can be much more general, and this is what we want to do. And to compute these elliptic genera uses then some dualities, M-theory duality and mirror symmetry, for example. So we consider here M-theory on an elliptic threefold X3. We want to compute these degeneracies of the elliptic genus. So we consider the 6-dimensional theory compactified on an extra circle, and then we have of these BPS strings, which we have here, certain quantities like the wrapping number. This is, we could consider wrapping number 1 only here. Then we have KK momentum and U1 charge. And these can be packed together abstractly in the elliptic genus that we want to compute. And this theory is dual to M theory in 5 dimensions, where this corresponds to a BPS particle in 5 dimensions, and it arises in M theory from wrapping an M2 brane over certain components of this compactification manifold. In particular, the KK momentum comes from wrapping the elliptic fiber, and then we have another curve which is responsible for the U1, and that gives the charge. Yeah? And these things maps into this kind of curve of the Calabi-Yau. This is, of course, a matter of mirror symmetry. So these invariants can be computed here with standard mirror symmetry and this elliptic threefold. And in the end, therefore, we can compute the elliptic genus in 6 dimensions formally by mirror symmetry of this threefold, and it's essentially given by the would-be prepotential in 4 dimensions. Yeah? So this gives a way to compute elliptic genera in a non-perturbative setting. Now, as I was already pointing out, elliptic genera have distinguished modular properties, and if we have an extra U1, then, and that was pointed out by Kawai et al. In the early 90s, the elliptic genera should be Jacobi forms. This means they transform nicely under modular transformations, and they have a modular weight W, but they also transform nicely under double periodic transformations in this fugacity, in this U1 field strengths. And there the transformation is characterized by M, which is the index. Roughly speaking, it corresponds to the Kac-Moody level of this U1, yeah? And it's an integer, even a positive integer. And in this setting here, it's given by a topological intersection number, namely C0, the curve we consider, times something which is called the height pairing, which defines this U1 in this elliptic Calabi-Yau. Yeah? And as is well known, these Jacobi forms are finitely generated, so we can write all elliptic genera just in terms of a finite number of basis elements of this ring, which are given here by the Eisenstein series and these Jacobi generators. And I already indicated that there can also be a quasi-modular Eisenstein function E2 appearing here, which has an important physical implication. So I assume that everybody knows this stuff more or less, so I don't need to be very specific here. Now, as I was saying, this quasi-modular Eisenstein series E2 transforms with a modular anomaly, so it has a shift transformation. And it's known from the mid-80s, actually Scheeleke and Warner were first to point out that this anomaly can be cancelled by this non-holomorphic completion, such that they have a non-holomorphic but modular covariant Eisenstein series E2 hat. And there's a physical interpretation, namely the geometry has a non-compact branch which has 0 modes, and in the full path integral one has to take it into account, and they provide this modular completion and makes a full partition function invariant. And this is very nicely illustrated here by these works originating from Minahan, Nemeshansky, Waffer-Warne, and later Hagehat, Lockhart, and Waffer. Namely, one can view the heterotic string as a bound state of two E strings. So to remind you, in the Horava-Witten picture, we have here the two end of the world 9 branes. The heterotic string stretches here. If we have an extra M5 brane, then we have also the E strings here. So in the sense, we can decompose the heterotic string into two E strings. However, there's a zero mode, namely the distance between these intersection points, these locations, is a zero mode. And that leads to this im tau, to this non-holomorphic independence. And therefore, the holomorphic anomaly of this elliptic genus, which is detected by taking tau bar derivatives of this partition function. And via this identity, the anti-holomorphic dependence only arises via E2. It's the same as taking a E2 derivative of the elliptic genus. That probes exactly, that detects this zero mode, namely the outcome of this derivative is simply the square of the partition function of the two E strings. So this gives a nice space-time interpretation of this holomorphic anomaly. And this is a very non-perturbative elliptic genus here we talk about because we have this M5 brane here. Now back a bit to more ordinary physics. I was already saying that in big gravity conjectures, we have a requirement that there exists a lattice in general of super extremal states in order for certain extreme black holes to be able to decay and avoid massive remnants. And just here in a particular example, here in 6 dimensions, we can plot here the charge and the excitation level. And the spectrum looks like this. And there are certain orbits here, spectral flow orbits, if you like. And here they are distinguished by this discriminant, which is just this index of this partition function, which is 2 in this particular example, times the excitation number minus the charge square. And this condition corresponds to extremal black holes. So if you go very far away up here in the excitation level spectrum, then these excitations should turn into black holes. However, there are extra states which are beyond this line, corresponding to delta equals 0. These are maximally super extremal states, and they don't have a smooth horizon. They are not black holes. And these states are exactly required in order for this massive, for the extremal black holes to be able to decay. And moreover, consistency upon compactification requires that these maximal super extremal states lie on a lattice, which is nicely seen here, charge lattice. And this property, this very figure is an automatic property of Jacobi forms. So whatever you do, so we started say from some F-theory compactification, make a certain limit, get a solitonic string out of in this limit, which can have non-perturbative components. And then in the end, we compute a certain part of the spectrum, the elliptic genus, and it's given by Jacobi forms. And just by how everything works, the outcome is exactly as it's supposed to be. So this is a nice relationship between mathematical properties and then physical requirements. So this so far was in 6 dimensions and very well known and understood in many years. Now I turn to new stuff in 4 dimensions, and the story is surprisingly more complex. It's extremely more subtle. So in 6 dimensions, in 4 dimensions, we consider n equal 1 supersymmetric theories obtained by F-theory compactifications on Calabi-Yau 4-folds. However, in order to have chiral spectrum, we need 4-flux switched on with certain requirements, some quantization requirements, and so on. And as I will say in the next transparency in more detail, the Gromov-Whitney invariants, which are the supposed degeneracies in the elliptic genus, they are intrinsically defined in relation to these fluxes. So in 4-folds, the Gromov-Whitney invariants automatically need a reference to flux, otherwise they're not defined. And as I was saying before already, the modular weight has to be -1 in 4 dimensions. And this means because elliptic genera, the Jacobi forms with odd index are antisymmetric, this means it vanishes unless we have a U1 field. Yeah, so that's why we consider U1 refinement. And what we will find is in treating interrelationship between flux backgrounds, Gromov-Witten invariance, modular properties of elliptic genera, in particular a new kind of holomorphic anomalies. And the whole thing is consistent with the gravity conjecture at the end, but more subtle. So here's some mathematical remarks, namely fluxes and Gromov-Witten invariance on Calabi-Yau fourfolds. So as we know, we count here maps from Riemann surfaces, the genus 0 in this case, into the second homology of this fourfold or k-fold in general. And we have a virtual dimension of the modular space, which must be either 0 or positive. If it's positive, we need to integrate over it. And unlike for threefolds, for fourfolds, we need to have at least one insertion. Yeah? And so one can loosely say, by looking to the details, that the invariants are pinned to the flux, and they are labeled by the flux. So there's intrinsic defining property of this Gromov-Witten invariance by this flux, which is an element of H22 of this 2,2 cohomology. And moreover, from this formula also follows that there are no invariants for genus larger than 1. Now, these invariants can again be computed via mirror symmetry. I don't spend much time on this here. I just say that H22 decomposes into a so-called horizontal or a vertical part. The vertical part just is generated by wedging 1-1 forms. And the horizontal part comes from varying the holomorphic 4 form. And like for threefolds, we can compute these invariants in a Kähler moduli setting via mirror symmetry in the complex structure-like setting where we just compute periods of, well, essentially we compute integrals of this kind of flux times holomorphic 4 form. Now, moreover, a bit more surprising is that if you talk about elliptic fourfolds, then we can define a variety of partition functions, which have different modular weight depending on the flux sector. So we have to go to a suitable eigenbasis of fluxes adapted to modularity. So this cohomology goes into 3 pieces, which has modular weight, formal modular weight 0, -1, and -2. And this refers simply, if we take these invariants and put them together and make partition functions out of them, then this partition function has the corresponding modular weight. Yeah? So the modular weight of this partition function depend on the flux sector. And I was just saying before, the elliptic genus in 4 dimension has weight -1. So in fact, only these fluxes lead to elliptic genera in 4 dimensions. What about the other ones? The other ones just correspond to prepotentials, which are obtained by type 2A strings and compactify them on a Calabi-Yau fourfold. So this gives 2-dimensional prepotentials or superpotential in this case. And so for all the fluxes, but only the -1 fluxes, -1 flux partition functions can be lifted to 4 dimensions. And then they become the elliptic genus of this F-theory compactifications to 4 dimensions. So if we now sit down and compute some examples, so we define a curve, a reference curve, and then we define trapping numbers of the elliptic fiber, which correspond to KK momentum, and so on, and define a flux, a -1 flux, for example, and assemble these partition functions, then one finds, extremely surprisingly, that the thing is not modular and also not double periodic. This is not a good Jacobi form. And by looking more closely, it turns out that actually there's a piece which is not an elliptic genus or partition function, but a derivative of a partition function of this kind. Yeah? And derivatives, of course, break modularity and double periodicity. Yeah? So it's well known that if you take a tau derivative of a Jacobi form, then we get a holomorphic anomaly or a quasi-modular piece represented by this E2 here, E2 extra component. And if we talk about Jacobi forms, then we get also E1 components, and E1 is sort of the quasi-modular friend of E2, and E2 is given by del log eta, as everybody knows, and E1 is given by well, then log theta 1. Yeah? And this kind of derivative is you know, the psi derivative as regard to the fugacity. It's just giving this kind of connection term. So this kind of modular functions are called QuasiJacobi forms. They are not QuasiModular Jacobi forms. Yeah? Typically, one writes QuasiModular Jacobi forms is being generated by the ordinary Jacobi generators times Eisenstein times E2. But here we have also on top of this E1. Yeah? And these things are called QuasiJacobi forms. And one can again now augment these, repair these deficiencies, these modular deficiencies by adding non-holomorphic pieces. E2 goes as usual, and E1 can be modified by adding this piece. And the statement is simply then that these physical partition functions, the physical for the elliptic genera, are such almost holomorphic Jacobi forms. Yeah. Now that, of course, immediately leads to holomorphic anomalies, namely we have this kind of quasi forms in the game of the non-holomorphic completions. So let me remind you, generically we have elliptic genus of this form. This is a fully modular piece, and then we have this derivative piece, which is the reason for the non-modularity, and this augmentation by this non-holomorphic piece can also be expressed by going to a covariant derivative here. So we add here this non-holomorphic piece. And then it's clear that the right-hand side will have a non-holomorphic, or the whole expression has a non-holomorphic component. And then we can have, of course, a holomorphic anomaly equation. We can take a derivative with respect to alpha and of this elliptic genus of modular weight -1. And the output is one of these other partition functions in a different flux sector, of modular weight -2. Yeah, so this is very surprising. So we have a holomorphic anomaly in the game, which links different flux sectors to each other. Yeah? And this is, physically, this is very surprising, but mathematically it turned out that this was known by works of Oberdick and Pixton a couple of years before. And this is a general properties of Kolmogorov invariance on Calabi-Yau fourfolds. Yeah? So what we have is a kind of algebra of anomalies. We have different flux partition functions, different in 2 dimensions a priori of modular weight 0, -1, -2. The -1 can be lifted to elliptic genus in 4 dimensions, and they're related either by del tau or the z derivatives, or the other direction by derivatives with respect to E2 or E1. Yeah? So we have this kind of structure here, operating between different flux sectors. Now one might ask, okay, this is just mathematics. I mean, now we really lose the connection to physics. So what can we make out of this? First question, of course, was holomorphic anomalies are well known from BCOV in the early 90s, where topological strings have been used and contact terms and so on, and in order to derive non-holomorphic dependence of partition functions. So one can repeat this game also for the fourfolds with fluxes. And it turns out that in this case, there's an extra term which has the form of a so-called gravitational descendant invariant in the language of topological 2D gravity. So this is the ordinary holomorphic anomaly equation according to BCOV. There's a quadratic piece which arises if this curve we talk about is reducible. This underlies this split of the heterotic string into 2 E strings in the end. But this is a new term. Yeah? It's a new term in this holomorphic anomaly equation. And one can now ask, okay, this is now a 2-dimensional physics. Is there a space-time interpretation of this too? And so let me remind you, before in 6 dimensions, we had this quadratic splitting term. So it was this term here, which was the basis of this holomorphic anomaly, which allowed to interpret the heterotic string as a bound state of 2 E strings. So the derivative of z is given by the square of the partition function of these 2 E strings. So the question is there a similar meaning in the present context of this extra term here? So we couldn't figure out this completely because it's quite complicated. but so conjecturally, and there's some evidence for this, that there are again holomorphic zero modes arising when the heterotic string meets an NS5 brane, and this there is a component of the modular space which is given by a certain threefold called Y3, which is embedded in the fourfold, which is non-obvious a priori. Yeah, so I have sketched here a little figure, but I don't explain it here. So there's a hidden threefold, and in favorable situations, this is actually a Calabi-Yau threefold, and in this case, this extra piece, is a modular object of modular weight -2. This becomes the elliptic genus of this threefold. Yeah. So in favorable situations, we have some kind of zero mode degeneracy hidden in this fourfold geometry with fluxes, which means there's a degeneracy which is labeled by this Calabi-Yau threefold, and this zero mode structure is captured or detected by this anti-holomorphic anomaly. Yeah. So this is the best interpretation we could give here. Now let's come back even to more down-to-earth physics, namely to the weak-gravity conjecture. I was just saying that the elliptic genus has two pieces in 4 dimensions, a modular piece and a derivative piece in general. Now, the properties of odd-weight Jacobi forms, a property is that they are antisymmetric, and therefore certain cancellations occur. And in particular, if you plot this charge mass spectrum, the maximal super extremal states don't exist. Yeah. They cancel out, disappear. Yeah. Moreover, there is a lot of other cancellations going on in the bulk of this spectrum. Yeah. And in particular, there's no lattice structure here. Yeah. So this, at face value, this looks like a violation of this tower weak-gravity conjecture. Yeah. But this sort of is remedied by at least formally, by this extra piece, namely this is non-modular, this quasi-modular only, QuasiJacobi. And because the Jacobiness is ruined by this, this actually feeds back these states. However, this is a very fishy argument because we talk about elliptic genera here. So if you see a gap here or a vanishing, it doesn't really mean that the states don't exist. They could cancel an elliptic genus. So we cannot really do better than this. Also, this is n equal 1 supersymmetric 4 dimensions. And we have quantum correction to take into account, and then it's also unclear what lesson can be drawn from this. But at least this is sort of from the modular point of view and from the geometric point of view, the best connection to weak-gravity conjectures we can do here. Let me conclude. The elliptic genera in 4 dimensions have surprisingly complex features. First of all, it's known that, well, they have to involve a U1 factor and must have modular weight -1. And one can compute them in non-perturbative settings from F-theory compactifications on fourfolds with fluxes. And one can compute elliptic genera explicitly by taking models and compute the fourfold Gromov-Witten invariance and assemble the elliptic genera. And then it turns out that these elliptic genera are not well modular. They have extra pieces, namely given by z derivatives of other partition functions, of other flux sectors, but sometimes they can also be hidden 6-dimensional elliptic genera in disguise. And this quasi-modular structure also leads to a new kind of, we call them elliptic holomorphic anomalies, which link together different flux sectors and also should have a very concrete interpretation of space-time. And I didn't have time to consider more physics applications. But one can do much more. In particular, one can study the phenomenon of, in this situation of non-perturbative anomaly cancellation, because as we know, anomaly cancellation is intrinsically tied to the modular properties of elliptic genera. Now, if these are not really modular, but have derivative pieces, one has to think about, what implication does this have to the Green-Schwarz mechanism in 4 dimensions? And this is also what we sorted out in this one paper. But that's all for today. Thank you.
Thank you, Wolfgang. And sorry, I didn't turn on the microphone, so you didn't hear people clapping. But maybe people can ask questions. Anyone online?
I should add, I couldn't come on Monday and Tuesday on Sunday because of I've been in another meeting physically.
All right. So if there are no further questions, let's thank Wolfgang again. We'll see soon in person. Thanks.
Thank you.
All right, we can move to our next speaker. Is she here? Irene?
Okay, hello, can you hear me now?
Sorry?
Yeah, can you hear me?
Oh, hello. So we can see you, but I'm not sure if we can hear you. Can you say something?
Okay, hello, hello, can you hear me?
We can hear you now.
Yes? Okay, let me share the screen.
Yeah. You should maybe try to speak up. Okay, so we have our next speaker. It's Irene Valenzuela, and she will talk about the progress in Swampland program.
Okay, can you hear me better now or it's too low? I can try if I talk like this or worse.
Better.
Better? Okay, I assume you are saying better. Okay, so then let me start. Thank you very much for the invitation to give this review talk. I'm sorry I cannot be there. I would have loved to. I'm sure the landscape is much better than here at my place, but hope to be able to go sometime in the future. So I'm going to give some review on the Swampland. I know that there has already been several talks on the Swampland program, so I will be brief in certain things, but still, since maybe, I don't know, some people don't know much about what these conjectures are about, let me explain anyway what the Swampland program is aiming, what is the goal, and then I will go slowly through the conjectures and the approaches, I mean, what we have learned about the conjectures in recent years following different approaches. Okay, so the goal of the Swampland program is to determine what effective field theories that are weakly coupled to Einstein gravity can be UV completed. Okay, so which ones are consistent with quantum gravity? And the point is that not everything can be UV completed. Okay, this is something that we already know in quantum field theory, but this constraint can become even stronger if we have gravity. Okay, so you have some EFT valid up to a certain cutoff. Whether this can arise from a consistent quantum gravity theory is non-trivial. And what we are seeing is that the consistency constraints that you need to impose seem to go beyond the usual anomaly cancellation, and is what we call Swampland constraints. Okay, so the typical picture is that if you have all the landscape, let's say all the EFTs that you could in principle construct that seem consistent at low energies, only a subset of them can arise as a low energy description of quantum gravity, like string theory, and the rest belong to the Swampland. Okay, so those that are not UV completed, then they belong to the Swampland. Okay, so of course, the tricky part is try to determine precisely what is in the landscape and what is in the swampland. So what are exactly these constraints? And this is, of course, a very ambitious program because we don't have a completely general framework of quantum gravity that we can just use to prove these constraints. But we can use all we have learned from string theory in all these years, and also arguments from black hole physics or holography to try to identify what these constraints could be, and then use all our tools, all the tools that we have at our disposal to gather evidence for these constraints. Okay, because if we manage to do it, I think the effort is worth it in the sense that we are giving what is the UV imprint of quantum gravity at low energies, and this can have also interesting phenomenological implications. Okay, so in the past years, there has been several constraints that have been proposed. Here I'm putting some of them. And what I wanted to remark now is that one of the most important developments, at least in my opinion, in the past 2 years, is that we are discovering more and more relations between the conjectures, which hint that there might be different phases of the same underlying quantum gravity principles that we are starting to discover, instead of just being independent random statements. So this generates some sort of internal consistency that can also help to understand one conjecture because of the relations I have with the other ones. And the goal, and this for me one of the goals, is try to understand better these connections so that we can try to reduce all these conjectures to the minimum number of principle or statements that could reproduce everything. Okay, so how do we do that? Well, there are many ways in which we can try to check the conjectures. So don't worry if you don't know exactly what they are. I will explain them in more detail. So as I was saying, there are many different approaches that we can take. And this is how we work in the Swampland program. Like, it's not just that we have some tools and then we use these tools to answer different questions. It's more like there is a community of people with different backgrounds and different research approaches that try to answer the same type of questions, try to gather evidence for these conjectures. So, as I like recently, what I'm gonna do also for this review is to focus on what are these approaches and what we have learned from the different corners. Okay, so I will start explaining a bit what we can learn from studying topological operators and cobordism and so on. And then how we test these conjectures from a top-down perspective of string theory compactifications. Then I will mention a bit recent developments in the context of holography, positivity constraints and black holes, and finish with some general remarks and very briefly maybe some implications. Okay, so let's start. See how much time. So I started 10 minutes late, right? Just to control the time. Okay, good. So the most important or the oldest conjecture that we have for the Swampland program is the absence of global symmetries. Okay, so it's the statement that any global symmetry must be broken or gauged in quantum gravity. The original motivation came from black hole arguments to avoid trouble with remnants. But there is also, why it's important is because there was also a lot of evidence from string theory itself, that there is no counterexample, there is no global symmetry that we know of. And this can even be proven in the context of perturbative string theory, or more recently in ADS-CFT for the case of symmetries that are splittable in the boundary. So even if this is a very old conjecture, actually in the past year, there has been several works about it because that are motivated by all the new soup of generalized global symmetries that is arising. that opens new avenues, no? To check whether they are realizing quantum gravity, and more concretely, what are exactly the mechanisms for which string theory avoids all these new types of symmetries. So just to put a bit, to set a bit of the context, the point is that if you have, for example, some U1 P4 global symmetry, so this is one of these generalized global symmetries, this is going to be characterized by some topological operator that I can, for example, write in this way in terms of a conserved current. And it's a P4 global symmetry because the charge operators, charge states, are supported on p-dimensional manifold. Okay, so the charges are not carried by particles, but by p-branes. So you have, for example, Maxwell theory, you can have a 1-4 global symmetry given by shifts of the gauge field, so that the current is the electric field strength. And then the charged operators are Wilson lines. Okay, these are the objects that are charged under the symmetry. So the charges are carried by strings, no, by one-dimensional objects. Okay. So the message is that we can learn a lot, not only from the presence, but also from the absence of this symmetry. So there has been a lot of activity studying these symmetries in quantum field theory, but also in the context of quantum gravity, there are many things we can say. Like, for example, I just wanted to remark one example in which we can focus on this, what we call Chern global symmetries, so that the currents are given by products of field strength. And then the point is that these symmetries in general are not easy to break because of the Bianchi identities. They are in pure gauge theory, they are typically conserved. So the way to get in which string theory gets rid of all these symmetries is non-trivial, and we can actually understand very familiar phenomena both in string theory and quantum field theory as consequences of avoiding these symmetries. Okay, so it's like a new reinterpretation of familiar phenomena like the existence of actions and Chern terms, the fact that there are localized degrees of freedom in monopole word volume branes, or the process of brane dissolving or rending on branes. All of these things can be understood if you want to require that there are no Chern global symmetries. Okay, now this example that I gave you is about, so we have some topological charges associated with the gauge field, but one could think more generally about topological charges also associated to gravity, right? Like more geometric things. And there is a well-defined way to talk about all these topological charges, which is in terms of cobordism classes. So thinking along these lines is what made Jake and Conundrum to conjecture that the cobordism group, that I will explain exactly what it is, of a quantum gravity theory must be trivial. Because otherwise, if it's non-trivial, the non-trivial cobordism classes would correspond to non-trivial topological charges associated to a B minus K minus 1 for global symmetry that should be forbidden in quantum gravity, where D is the total dimension and K is the internal dimension. Okay, so it's a bit hard sometimes to define what is this quantum gravity cobordism, but at least the low energy, like the classical correspondence, the geometric meaning is clear. It's a well-defined object in mathematics, and it means that if you have two manifolds, they are in the same cobordism class, so they are bordered to each other. If you can write their union as the boundary of a manifold of one dimension more. Okay, so this is something that already I think Miguel explained in his talk because it's useful for anomalies, but it also connects with the absence of global symmetries. Okay? And if a manifold is a boundary by itself, then we say it belongs to the trivial class. Okay, so the statement that the cobordism group vanishes, it means that if I consider the two effective field theories that arise from compactifying, for example, string theory on these two manifolds, I'm gonna get two effective field theories, and the fact that there is this covordism, that they are in the same covordism class, means that there is a domain wall connecting the two EFTs. Okay, and in the case of the trivial class, what happens is that I have like an end of the wall brain. Okay, so it connects to nothing. So we can replace, or we can give a physical understanding of this conjecture as the statement that all effective field theories of the same dimension, all EFTs, are connected by finite energy domain walls. So everything should be connected to each other. Okay, and that's what it means, that everything in the same, the covordism group is trivial. So one can use this to predict, for example, the existence of new defects in string theory, like new, like associated with domain walls that can be even non-supersymmetric, because they would be necessary in order to avoid some topological charge, some global symmetry. Okay, so this covordism group has been used in many different ways. So I'm gonna just mention two. One is that it has been very useful in the program of what we call string universality or string lamppost principle, which aims to show that any EFT that is consistent with quantum gravity actually arises from string theory. Okay, so it tries to answer the question to what extent string theory is universal, in the sense that we can get everything that one should be able to get that is consistent with quantum gravity. And I mean, this is a very important question. Of course, we don't know the answer, but there has been a lot of recent work trying to check this, at least in the context of having a lot of supersymmetry, where things are better controlled and we can classify what is possible and what is not. So using Swampland constraints, anomaly cancellation, also these covordism groups and supersymmetry, these works are showing this string universality in the context so far of 16 or 8 supercharts. Okay, the other quick application I want to mention is that it's related to the instability of the vacuum. Okay. So the point is that there are these bounds of nothing that we also had to talk about, which corresponds to non-perturbative instabilities, in which a bubble of there is nothing inside pops in and starts expanding and describing the instability of the vacuum. And the thing is that these bubbles of nothing are very interesting because I think they could provide some sort of universal instability when certain conditions are satisfied. So one of the conditions you need to satisfy is that it has to be allowed topologically, which means that there's a compact space that has to shrink at the boundary of the world. So why this solution is possible and why this solution is smooth is because even if there is nothing inside, there is some compact dimension that it shrinks to zero size, so that the full solution is smooth. So we need to be able to shrink the space, and this is something which is precisely characterized by this covordism, because this is possible whenever this compact space belongs to the trivial class in Bordism group. So if this covordism conjecture is true, that is the covordism group is trivial, it means that every manifold belongs to the trivial class, which means that it's always possible to shrink the manifold to a point, which means that it's always possible to construct a bubble of nothing, at least at the topological level. Okay, so there is no quantum gravity abstraction for that. Now, of course, once you have this at the topological level, you have to check whether the bubble will expand. And this is related to whether a certain energy condition is violated at the semi-classical level. Okay, and the expectation is that these energy conditions are violated whenever supersymmetry is broken, which can give rise, therefore, to a connection between this covordism conjecture and the Swampland statement that any non-supersymmetric vacuum should be able to decay. Okay, so this is a statement. I will not talk much about it. It's just a conjecture that was motivated by the weak gravity by very different means. But now we've seen that it can also be correlated to the absence of global symmetries thanks to this covordism conjecture. Okay, so this is one example of the relations I was talking about. The other example I want to give also is the relation between this absence of global symmetry and the completeness hypothesis. Okay, so the completeness hypothesis is also quite old as the absence of global symmetries. And the statement is that the spectrum should be complete in the sense that all physical charged, that there should be physical charged states in all the possible representations of the Gauge group that are consistent with Dirac quantization. So the question that we were trying to answer is whether this just follows from the absence of global symmetry. So to what extent we can unify both conjectures into a single state. Okay, and this is a question that actually can be answered in a very rigorous way already in the context of quantum field theory, because we can just translate the statement of no global symmetries to the statement that I don't have topological operators. No, I was discussing that every global symmetry will be described by some topological operator. And we can also translate the statement of having a complete spectrum to the statement that all these charged operators can end. Okay, so let me explain this a bit. So the point is that if you have, for example, Maxwell theory, I told you that the symmetry operator is given by the exponentiation of the current, which is the field strength. So this describes a one-form global symmetry. And the object that is charged is a Wilson line. Now, if this Wilson line can break in the sense that, for example, I have charged particles in my spectrum, then I can always shrink, unlink this symmetry operator, this U operator, away from the Wilson line and shrink it to zero size so that it becomes trivial. So, and therefore it cannot be topological. It would be inconsistent with the fact that it's topological, because the result of the linking of this symmetry operator with the charge operator should be something, should give you a non-trivial result. Okay, so a way to break a global symmetry, so to render this operator non-topological, is to have charge states such that this Wilson line can break. Okay, so the one for global symmetry gets fully broken in the presence of a complete spectrum of charged particles, in the case of Maxwell theory. And therefore, you can see here that both conjectures need to be correlated. The fact that Wilson lines can break, so I have charged states, and the fact that the operators, the symmetry operator is no longer topological, so I don't have a global symmetry. Now, you could ask whether this is completely general or it's just an artifact of the Maxwell theory that I described. So whether no topological operators is always in one-to-one correspondence with the statement that all extended charge operators can end, so that I have a complete spectrum. And the answer actually is that this is not true in general. Okay, so it's true for continuous gauge groups, but it's not true in general for discrete or disconnected continuous groups. So you say, okay, so that's it. There is no correlation then, but there is a way to save it, which is very interesting, which comes from generalizing this notion of symmetry. Okay, so I'm saying that there is a lot of activity on generalizing our notion of symmetry in quantum field theory. One of the corners, one of the possibilities of generalization is to consider non-invertible operators. Okay, so what are called non-invertible global symmetries. So these are symmetries whose symmetry operators do not satisfy a group law. Okay, so I don't have a symmetry group anymore. It's a more complicated fusion algebra, but still there is a topological operator. There is an operator that is topological, which means that there is a transformation that commutes with the Hamiltonian. It's kind of a symmetry in the same way. And you also have operators that are charged under it. So this is what are called non-invertible global symmetries. And interestingly, it seems that if we allow for this generalization, then we can show that there is a correspondence with the completeness hypothesis, with the fact that the spectrum is complete. So these one-to-one correspondence have been proven for the case of discrete gauge symmetries in 3D QFTs. And also recently, we proved it for the case of the electric symmetry that you have in a general compact gauge group that is just coupled to matter. Okay, so there are no Chern-Simons terms, it's isolated. and the analogous for the magnetic symmetries and twist vortices. So the goal in the future would be to continue generalizing these proofs to try to show whether this statement is completely general by when having both electric and magnetic symmetries considered simultaneously. Okay. So I have told you how, like the recent development that we have in the context of no global symmetries, that it seems the modern notion is that we should replace this statement by the claim that there are no topological operators in quantum gravity, so that we can also include these non-invertible symmetries, or more generally, that there are no covordism classes. And of course, now the goal is also try to understand why this is the case, no? In more general context. In this direction, I can at least mention that it's not so surprising, maybe when written in this way, because topology itself is something that is dynamical in quantum gravity. We have topology change all the time. So maybe, this is somehow behind the fact that there are no topological operators, and there's no way to define these properties. It's a concept that only makes sense in quantum field theory. Okay, this also connects with recent developments to prove the absence of global symmetries based on black hole unitary evaporation, in which it was shown that precisely this topology change is essential to understand this black hole evaporation, this unitary derivation, this derivation of the unitary page curve that have happened in the community. And people have shown that this is also, if you have a theory in which the page curve is unitary in the way they describe, so that black hole evaporation is unitary, then this also forbids global symmetries, and the replica wormholes and all these things that they use to show this unitary page curve, they violate the global symmetry. So it can be shown that they violate it, and more generally, topology changing processes tend to violate all these global symmetries, and that would explain why we don't have global symmetries in quantum gravity. Okay, very good. So this is what I wanted to say about all these exact global symmetries. And from now on, we will focus on approximate ones. Okay, so what happens if the symmetry is not exact, but it's approximate, and whether we can quantify how approximate can be. So how much we have to break. Okay, so let me explain this a bit, because I can use this to define the other two most important conjectures that I'm going to review, which are the weak gravity and the distance conjecture. So the idea is that, okay, it's very nice, maybe it's already quite well motivated that we don't have global symmetries, but maybe this is not super useful for phenomenology because we can always break it at a very high scale. Can we quantify how close we can get to restoring a global symmetry? So, for example, one way to think about this is that if we move in the model space of string theory, so if we change the parameters of our effective theory and tune the parameters, move in this space such that we approach some point that would restore a global symmetry, something has to go wrong because we don't have global symmetries in quantum gravity. And the way this is solved in string theory is that this point that would restore a global symmetry is pushed to infinite distance in this field space. And not only that, but that as we approach it, the EFT is breaking down in a continuous way. Okay. So the cutoff of the effective theory should go to zero as we approach these points in which one would restore a global symmetry. So that at the infinite distance point, the cutoff is zero. And there is no description that makes sense. Now, how exactly this cutoff goes to zero is quantified by the distance conjecture and the weak gravity conjecture. So the distance conjecture is the statement that there is an infinite tower of the states that become exponentially light at every infinite field distance limit of the modular space. Okay, so because we cannot have infinite many fields with decoupled constant gravity, this is going to imply a drastic breakdown of the EFT. So quantum gravitational effects become important and this quantum gravity cutoff goes to 0 exponentially. Okay, so it tells you how it goes to 0. Now, in practice, this implies an upper bound on the field range in terms of what is the cutoff of your theory. Okay, so the higher the energy you want to describe, the smaller the field range you can accommodate. And one of the main open questions in this conjecture is exactly what is this exponential rate? Okay, so how fast goes to 0? So I will show you that in recent years, we have made a lot of progress understanding exactly what this factor can be. Now, for the weak gravity conjecture, that we have already heard talks about it. This conjecture tells us that given a gauge theory, there must exist an electrically charged state with a charge to mass ratio bigger than the charge to mass ratio of an extremal black hole. Okay, so this is what we call the mild version. Strong version is that we don't have just one particle, but we need to have a sublattice or a tower of super extremal states. Okay, and this is motivated by consistency under dimensional reduction in string theory, also modular invariance of the CFT, and unitarity and causality. So the weak gravity conjecture, should be valid everywhere in the modular space, but it's precisely when we approach these points, these weak coupling points, where a gauge coupling goes to 0, and we would restore some global symmetry, that becomes more important for phenomenology, because then it means that we have new light states, no? Because the charge to mass ratio has to be bigger than an order 1 factor. So they become light if the charge that depends on the gauge coupling goes to 0. And this is another example in which indeed we can see that when we try to restore a global symmetry, then something goes wrong. So we have these new states and the cutoff of the EFT goes to 0. Okay. So these are the two conjectures. The message is that, we can have approximate global symmetries with the coupled gauge theories, large field ranges, but if we try to have these things, they come at a price, in the sense that the UV cutoff should go to 0, new physics should appear, and not only that, but also these new light physics imply some constraints on the EFT, in the sense that there are some universal patterns that appear also on the interactions and the scalar potential and so on, that seem to be universal at every asymptotic limit and might be triggered by these new light states that emerge. So it's important to emphasize that this is valid at every infinite distance limit. It's not just about weak string coupling, so it's not just about perturbative string theory. It's any infinite distance limit. And understanding these universal patterns that are generated by the towers of states becoming light is what gives rise also to many of these relations between the conjectures. So just to put a bit of order in this map, before we were discussing the first row on the top, which is about the kinematics of the EFT, it's about exact global symmetries. And then we have the weak gravity and the distance conjecture, which constrain the spectra. They tell you some properties of some new towers of the states that emerge. And then we have, at the end, I will discuss a little bit about these other conjectures that constrain the scalar potential, like the interactions of my field, and can be also related to these towers of states. Okay. So let me, we already are halfway through or more, so that's good. So let me give you a little bit some review of how we check these conjectures. Okay, so especially this with gravity and distance conjecture, how we check them and what we have learned about them in recent years, coming from string compactification and also holography and black holes. Okay, so it's important, I think in the Swampland program, it's important to check these things from many different perspectives. So it's useful to have all these black hole arguments and so on, but it's also important to check them explicitly in string theory examples, because this helps to sharpen the conjectures and fix all these order 1 factors that are not determined sometimes. And by doing this, for example, we've been able to give concrete lower bounds for the exponential rate of the tower of the distance conjecture. So just to give an example, in the case of Calavian threefold, we can give a lower bound for the exponential rate of the tower, so how fast it becomes light, which is fixed by the discrete monodromy symmetries that are associated to each infinite distance limit. Now, it's also useful because actually by studying these conjectures, we have uncovered new geometric properties of the compactification that we didn't know, and it gives rise to many interesting connections also with mathematics. Okay, so this has triggered a lot of research on these mathematics properties and these geometric properties. And just to give some examples, like now we have some systematic classification of all infinite distance singularities in Calabi-Yau manifolds using Misford structures, and which has also given rise to this notion of moduli space holography. So to see to what extent one can characterize, one can determine the geometry deeper in the moduli space from the information that we have at the boundaries, at these infinite distance boundaries. And also in the previous talk, for example, we learned about interesting connections between algebraic geometry of Calabi-Yau and modular properties of QuasiJacobi forms that was triggered also by these Swampland conjectures. And just an example that, for example, there are these infinite flop chains in M theory in Calabi-Yau threefold that if you study the distance conjecture there, you can see that it's correlated to a previous mathematical conjecture by Kawamata and Morris. Okay, so this is one of the things that people have been doing. Also, I think one of the things that we understand better now is to identify properly what are all these towers of states, so that we can check rigorously the distance and the weak gravity conjecture at these asymptotic limits. Now, for the case of more than 8 supercharges, this is proven that you are always going to have these towers of previous states. For the case of theories with 8 supercharges, it was not so obvious, and there has been a lot of work in the past years to gather evidence for this and identify the towers and exponential rates and everything. So I think at the moment we have a very good, solid understanding of what's going on with 8 supercharges. And the next step that we've been working on is what happens in theories with less supersymmetry. So for the n equals 1 EFTs, for example. Now, Luca already gave a talk about this, so I'm gonna skip this part. Just wanted to mention that in 4 n equals 1, it seems we always have some string that becomes tensionless at infinite distance, and this is what allows to the distance conjecture and the weak gravity conjecture to hold, even if it's not the leading tower. Okay, so this is just 2 comments. One is that we always find some intriguing relation between the leading tower and the tension of the string, such that they relate by this integral power. It's not very clear why. I think it's gonna be related to the fact that the possible limits that we have is very constrained in the end, and is related to what are the possible dualities that we have in the string here. So whenever we have these towers of states, they make manifest some string duality. And I think probably these exponential rates can be related to what are the possible dualities that exist. And also, just a comment, this can be used to provide actually the existence of the strings can be used to provide a bottom-up derivation of the distance conjecture using the weak gravity. And using that, we can map this infinite distance path in modular space to RG flows of the string. Okay, so I will not say more because Luca already gave a talk about it. Let me just then summarize what are the lessons, I think, or some of the lessons that we get from studying these conjectures in string compactifications. Okay, so the first lesson is that the nature of the tower and the exponential rate are very constrained. So even if they are not specified by the conjecture, in all the examples we have checked, is extremely constrained. Like, for example, the nature of the leading tower seem to be always either a sort of keiki tower or a string, a string tower, no? Excitation modes of a string. And this is what is encoded on this emergent string conjecture. But also the exponential rates are very constrained. Like typically, for example, in Calabi-Yau 3-4, we only get 3 possible values that are related to the main 3 types of infinite distance limits that we have. Also, so far, all the limits are weak coupling points. Like there's always some P-form gauge coupling that goes to 0, which means that it's the same tower satisfying the distance conjecture, also satisfying the weak gravity conjecture. So maybe there is just one statement in the end that it's valid at the asymptotic limits. And also that by studying these conjectures in string theory, we have, there have been some proposals about what would be the bottom-up explanation for the distance conjecture. So why, this is something that is, let me say, so the existence of these towers is very well known. Like we study a lot in string theory, and it's very natural from the string theory perspective because it's connected to all these dualities that we have, like T-duality, S-duality, and all these things. But it's not clear at all why it's true in general. Like there is no clear motivation based on black holes and other things why the distance conjecture should hold for any quantum gravity field. And there are proposals based on the fact that, for example, it seems that we always restore some global symmetry asymptotically, so might be related not to this, to having a quantum gravity obstruction to restore a global symmetry, as I said. There is also the emergence proposal, which flips the logic of the conjecture by saying that the infinite distance and the weak coupling emerges from quantum corrections of integrating out the tower of states. Okay, so in the end, the infinite distance is a consequence of having the tower of states. And in this context, even if it's not motivated by string theory, I wanted to mention also this recent work by John Stout, which generalizes this notion of distance in terms of distinguishability of the fields. So, the fact that two theories can be distinguished by immediately by some experiment should imply that they are at infinite distance. And he can also connect this infinite distance with having this tower of states as we do with the emergence proposal. Okay, so let's see how much time do I have? Okay, I think I have, if I'm not mistaken, 20 minutes probably because it started 10 minutes late, so including questions.
20 minutes.
Sorry? What did you say, 20? Okay, I cannot listen very well, but I am assuming it's more or less that, including questions. So I will try to finish before. Okay, so that's fine. I think I'm fine. So let me just say very briefly one last thing about the distance conjecture, which is that so far I was focusing on flat modular spaces, but you can also ask what happens if you have a scalar potential and whether the values of the potential should still satisfy the distance conjecture, because these values might not be UV geodesics. Might not be geodesics from a UV perspective of the flat modular space, but more like axiom monodromy trajectories and all these things. So to answer this question is essential to see if the distance conjecture has implications, for example, for inflation. Okay, when we have the scalar potential. Now, in principle, the answer that we expect is that, yeah, the values of the potential should satisfy the distance conjecture by consistency of the distance conjecture at any energy scale, because we could always integrate out the heavy directions and get a new modular space in the IR, no, just given by this value. And the distance conjecture should not care about what energy scale you are checking things, right? It should be invariant under it. Now, if this is true, it's highly non-trivial because it implies constraints on the potential that are consistent with quantum gravity, because not every valley, like not every trajectory should be allowed, because maybe some very turning trajectories do not satisfy the distance conjecture. So it puts non-trivial constraints, and that we have, for example, checked in the context of Calabi-Yau Flux compactifications, and we know that at least there they are satisfied. Okay, so an interesting question is whether we can check this in more general other setups. And also let me mention that this perspective of having the RG flow in 4n equals 1 is also valid in the presence of a potential. So it really hints that it doesn't matter whether you have a potential or an exact modular space. Okay, so let me just go with the last part, which is the fastest one, which is what we have learned about these conjectures from the context of holography, positivity constraints, and black holes. Now, from the context of holography, it's very useful sometimes to reformulate these conjectures to statements on the CFT, because then we can aim to prove these conjectures using conformal bootstrap techniques. And the Swampland program and the conformal bootstrap are actually very interconnected, because in both cases, we are trying to understand what is the space of consistent quantum gravity theories, right? In one case, it's like quantum gravity theories that are associated to Einstein gravity. In the other case is quantum gravity theories which has an ADS, no, that are in ADS back. But it's very similar, and there is a lot of overlap between both programs. And this, for example, have been very useful to give evidence for no global symmetries, or also for the weak gravity conjecture using modular invariance in CFT2. Now, more recently, we have also translated the distance conjecture in the CFT and formulated what we call the CFT distance conjecture. Okay. So here, what we see is that there is a correlation between these three notions. So whether a given point is at infinite distance in the conformal manifold by measure with the Samolov-Hikov metric, and whether this point is a free point, so there is some bit coupling that goes to 0, for example, and whether we have a higher spin tower. Okay, so the point is that, so the conjecture is that there is always some tower of higher spin operators whose anomalous dimension decays exponentially in terms of the distance measured by the Samolov-Hikov metric, as this distance goes to infinity. Okay, so as we approach one infinite distance point. So this is the analogous to the distance conjecture. And here, some of these correspondence can be proven explicitly. So for example, the fact that whenever we have a higher spin tower, this corresponds to a free point is something proven by Maldacenas y Boedo follow-up papers. In the context of superconformal field theories, we can show that this free point corresponds to sending a gauge coupling to 0. And then in superconformal field theories, we can prove that because we send the gauge coupling to 0, we can compute the Samolov-Hikov metric perturbatively and show that the point is always at infinite distance. Okay, so whenever we have this higher spin tower, this is going to generate an infinite distance point. And the opposite is less trivial, so that's whether this is the only way, no, to generate infinite distance. And so far, I mean, we have not been able to prove it yet, but it's supported by all known examples in superconformal field. Okay, now if there is a weakly coupled ADS dual, this CFT statement translates indeed to a stronger version of the distance conjecture, because we are specifying the spin of the tower. So it's not just that we have a tower, but there's a higher spin tower, so a tower of higher spin field with an exponential rate that can be computed explicitly in the CFT, and is given by the central charge over the dimension of the gauge group that becomes free. Okay, so it gives an interpretation about what is this exponential rate in terms of what portion of the theory is getting decoupled from the rest. Okay. And well, of course, since the dimension of the gauge group can never be bigger than the central charge, this exponential rate is always lower bound. So we can give a universal lower bound for ADS, for these infinite distance limits in ADS. Okay. So this CFT distance conjecture in principle is valid beyond Einstein gravity, which also opens the question of to what extent some of these Swampland conjectures are valid beyond Einstein gravity. Might hint sometimes deeper principles that are of quantum gravity. Okay, and to finish, let me mention a bit what we know from black holes. Okay, this will be the last point, and then I will just conclude. Okay, so there are also, I mean, another way to approach all these Swampland conjectures is try to use general arguments that are independent of string theory, because in the end, if we are trying to say that these conjectures are general for quantum gravity, we should understand, give some general explanation for them, right? That is independent of string theory. And a way to do that is using positivity constraints and black holes. So for example, there is a lot of recent work, very interesting work, coming from people from the conformal bootstrap community that are now using all these techniques to constrain the S matrix and give bounds on the higher derivative terms of effective theory that are weakly coupled to gravity. So this is very correlated into the Swampland program. I'm sure that in future years we will hear a lot about this, and maybe we can prove some of these conjectures using these techniques as well. Also, I mean, this is not the first time that these positivity constraints are used, no, to prove this conjecture. Like, for example, the weak gravity conjecture can also be argued from studying positivity constraints on the higher derivative corrections to black holes. Okay, that can show that at least a mild version of the weak gravity conjecture is satisfied, in the sense that small black holes will receive corrections that will make the charge to mass ratio bigger than 1, no, bigger than the extremal value for a large black hole. And the goal is try to understand exactly what are the what are these positivity constraints, whether unitarity and causality is enough to show that this charge to mass ratio becomes bigger than 1 or not. And there are recent works also in the context of not just mass-word theory, but adding scalar fields, in which it seems that unitarity and causality is not enough, but it's enough once you require some additional structure, like for example, having a SL2C symmetry or some duality symmetries or things like this. So this is another avenue to try to prove the weak gravity. And we can also check it explicitly using black hole solution, right? So in this context, there is also a lot of work adding scalar fields. Okay, so it's, I mean, the weak gravity conjecture without scalar fields is more obvious, but once you add scalar fields, it's much more tricky how to define it, because then this super extremality condition, you know, that is used to show that, I mean, to give an argument for the gravity conjecture, in the sense that black holes should be able to decay, and that's why you need to have this particle with a charge to mass ratio bigger than 1. So this super extremality condition becomes different to the other motivation of the weak gravity, which is sort of a repulsive force condition, so that the gravity is the weakest force. So these two notions can be different in the context of scalars, but recent work show that they are equal for extremal black holes and also for the towers of asymptotically massless states that we get at the weak coupling points. And this is very interesting because it's precisely this correlation between these two notions of super extremality and this repulsive force condition, that gravity acts weaker, what implies that if I have a Gibbs coupling, a P-form Gibbs coupling that vanishes at infinite distance, the same tower that satisfies the distance conjecture will satisfy the weak gravity conjecture, and one can use the extremality bound of the black holes to lower bound the exponential rate for the tower in the distance conjecture. Okay, so this is something that we check a lot in examples, and I believe that there is always some P-form Gibbs coupling at the infinite distance limit, which would mean that we can always bound the exponential rate of the tower using this black hole extremality, which will be very interesting because then there are no more free parameters in the conjectures. Now, finally, just to finish, there are also works like studying, I mean, the same way that I told you, you can study these black holes with the scalar fields, we can also study black holes in different contexts, for example, in the zeta. And by studying black holes in the zeta and requiring, again, that black holes should be able to decay without becoming super extremal, so without generating a naked singularity, and applying this to large black holes in the zeta, this gives rise to this Festina-Lente proposal, which shows that it's not enough the usual weak gravity, but you also need to require, for this to be possible, that all charged particles satisfy this inequality, so that the mass is bigger than the gauge coupling times the Hubble scale. So it seems that the weak gravity conjecture in the context of the sitter is stronger. It gives more constraints than what we usually have in flat space. And it's just interesting, no, to understand what are the phenomenological implications of this. And furthermore, very recently, there is a paper by Harlow and Woody, in which they give also a new argument in favor of the distance of the weak gravity conjecture based on black holes in ADS. So they argue that indeed black holes, even if they are small, cannot be stable. They should be able to decay. So you need to have these particles satisfying the weak gravity conjecture, because otherwise they would imply a violation of charge quantization. So we have more and more arguments and evidence for this conjecture in different contexts. And this is what completes this map that I showed you at the beginning regarding these three important conjectures: the absence of global symmetry, the weak gravity, and the distance conjecture. Okay, so we'll have 3 more minutes or 4 more minutes? Or should I already finish?
No, it's okay. 3 more minutes is fine.
Okay, so if I have 3 more minutes, I'm gonna say a few words about
Go ahead.
About the lower row. Just 3 minutes is enough, and then we conclude, and we can see if there are questions. Okay, so these are the ones I put in purple are the most important conjectures. That's why I spent all the review talking about them, because all the others, are actually generalizations, or like you can understand them as applying this conjecture to different corners. And I mentioned a bit the fact that any non-supersymmetric vacuum should be unstable, but I didn't say anything about these other 3. So I just want to very briefly mention them and explain what is the status. So at the moment, the approach to test this conjecture is just based on string compactifications, like try to understand whether they are satisfied or not. And unlike for the previous conjecture, which we already have a lot of evidence for them, the situation here is less clear. Okay, this is still work in progress, and one is trying to sharpen and understand what is the precise statement that is realized. Okay, so just very quickly, for example, the ADS distance conjecture deals with the topic of scale separation in ADS. So whether we can have scale separation between the ADS scale and the internal dimensions. And the idea is that if one generalizes the distance, not just moving in modular space, but to the space of metric configurations, one can show that the flat space limit is at infinite distance, and therefore, according to the distance conjecture, one would expect to have an infinite number of states becoming light, and that will scale with the cosmological constant in this way. So that if you try to take the flat space limit, then the theory is going to break down because you have this tower of states. And if this exponent is bigger than 1/2, you are not going to have scale separation if the tower corresponds to the KK tower of internal dimensions. Now, this has triggered research in string constructions. There are possible counterexamples to the strong version, but not to the mild version. So just to the value of the exponent, what is not clear. And also recently there is a potential counterexample, not to the conjecture, because there is no family of aqua, but to the idea that maybe there is no scale separation in ADS, which is given by this KKT vacuum with a small W. Okay, so this is still in process, and the same for the sitter. So the sitter is the other big topic in the Swampland program, whether we have the sitter in quantum gravity or not. And here you can wonder whether you have the sitter first at the asymptotic limit. So whenever we have these towers of states, because this is something that one can check rigorously and is very well under control, and surprisingly it's not excluded yet. Okay, so it's not excluded, but at the moment, what we always find is there is always this runaway behavior as you approach one of these infinite distance boundaries, which is like a generalization of the time saver problem. And the potential seems to satisfy always this constraint on the slope at the asymptotic limits. Now, this is consistent with no goals, and what people try also to determine exactly what is this factor from string theory setups, and there are some proposed values that let me just skip. And the goal, I think the main goal is to understand why this happens. So why we always have this runaway behavior in general, like why this is a general feature of quantum gravity. So at the moment, all we have are relations to the other conjecture. So for example, one can show that this runaway might be triggered by the towers of states that are becoming light. And also by, in the context of 4n equals 1, where the potential comes from fluxes, you can show that comes from the fact that the membranes that parameterize the scalar potential, the superpotential, saturate the gravity potential. Okay, so this is all for the asymptotic limits. Now, this, I want to remark, this is just for the asymptotic limits. Now, the next question is what happens beyond parametric control when you go deeper into the modular space. And then there is all this story of KKT, last volume scenario, whether there is a 10-dimensional uplift or not. There are many recent works that I'm going to discuss. Just wanted to mention that it might be that there is the sitter deeper in the bulk. I mean, it's not excluded at all. And I think the main question then is how metastable can it be? So there is also this proposal that tells you that this, if there is a de Sitter vacuum, should be short-lived in comparison to Hubble. Okay. So this is it. I'm back to this diagram of all the conjectures. So let me just conclude. We have this web of interconnected conjectures. These were the three most important ones from which we can derive many of the other things. We discussed how the first ones can be unified in this notion of not having topological operators or endability of everything, while the other ones quantify how much you can break it. And there were like different generalizations of the weak gravity conjecture, no? From applying this conjecture to different setups, new ideas that have appeared. This is just a summary that you can see in the slides later on if you wish. And then the Sitter part. So the point is that we have this web of interconnected conjectures that we are starting to understand better and better. They can give rise to phenomenological implications that I have not discussed in this talk, but we can see the reviews for that. And I think it's important, I mean, precisely because of all these possible phenomenological implications, it's very important to gather more evidence, no? Solid evidence for these conjectures, using all the tools that are at our disposal. So these are just all the approaches I described, and it's important to address the issue from different areas, because it's only when we gather evidence from different corners and different approaches that we start believing that there might be something there, and hopefully be able to connect eventually string theory to the real world. Because if there are new constraints that need to be satisfied at low energies, this can give new guiding principles to progressing beyond a standard model, and also change the logic of naturalness, okay? Because not everything is allowed. So all these notions of fine tuning and all these things should be revisited once we know what is the actual space of parameters that is consistent with quantum gravity. Okay, so thank you very much for your attention, and let's see if there are questions.
Irene. All right, some questions maybe? Dieter.
Irene, can you hear me?
Yes.
Yeah, thanks for this very nice talk. The Swampland rules, they should be valid in general quantum gravity theories. However, the tests, it seems to me, are exclusively done so far in string theory. My question is, are you aware of any tests that go beyond string theory, which are outside string theory?
Yeah, so that's, I mean, that's one of the big questions, right? So yeah, I agree. Most of the evidence comes from string theory. Not only, no, that's why I put, for example, here all these approaches. Like we have arguments based on black hole physics, positivity constraints. I mean, this is more general beyond string theory, and that's why we believe that these constraints are constraints that could apply in general to any quantum gravity theory. Now, it's not clear whether the resolution is that they apply to any quantum gravity theory regardless of string theory, or because string theory is universal in the sense that everything somehow is connected to string theory. This is what is called this string universality. My opinion is that I prefer not to take a side. I mean, I think both cases would be super interesting. I mean, either because we can use these conjectures to distinguish string theory from other completions, or because in the end, these concepts apply to any quantum gravity theory because everything is related to string theory. I think both outcomes are great. And I think time will tell. And it's one of the things that we have to address within the Swampland program. So we'll see in the future.
What's rather specific, I know that the rules are from general quantum gravity considerations, often from black holes. Do you know of any specific tests outside string theory so far?
Well, I think, I don't know, I would say that some of these black holes are also outside string theory, but if you wish, like maybe the ones that are more, I mean, probably all these positivity constraints, like coming also from the S matrix bootstrap, I think it's a very interesting avenue to test these conjectures beyond string theory, because they just rely on unitarity and causality and this type of things. So yeah, so I would say either, yeah, because positivity constraints or related things that will rely on unitarity, causality, and things that we expect that any quantum gravity theory should satisfy, or black hole arguments that, at least in my opinion, might be more general, but I agree one has to check exactly which one. Like whenever we have black holes, this is already like an experiment. We can test all these quantum gravity ideas. But yeah, probably the first one is more general. And I think it should be possible. I don't think why not. I mean, I think we are very close also to prove the absence of no global symmetries. I mean, there's a lot of progress in this regard, also using this type of arguments coming from unitarity and causality and black holes, and also from holography. So I don't think it's impossible, but I mean, in general, I'm a very optimistic person.
There is more coming.
Finally, very quick, did anybody ask you already about loop quantum gravity?
Yeah, people have asked sometimes. I mean, these are like the typical things. We'll see. I always say, well, you can check, as I said, you can check whether these conjectures are satisfied there or not, and therefore whether they could distinguish string theory from loop quantum gravity, or whether maybe they are also satisfying loop quantum gravity or other. I mean, sometimes I've given talks invited by people working on other alternatives for quantum gravity completions beyond string theory, because they were interested on trying to check whether these conjectures are satisfied there. Like also asymptotic safety and all these things. And might be that they are as well, if we really think that they are more general, and these are valid quantum gravity completions. So it depends on that. But it's worth to check to know what is the answer anyway.
All right, thanks. There are more questions. Yeah, please.
Can you hear me? I turned this on, right? Yeah. Hi, Irene, it's Ivano.
Hello, Ivano.
Hi. So I have a couple of questions on the distance conjecture, but first, since Dieter and you started discussing about this, maybe it could be interesting to mention one of my recent papers about testing Swampland conjectures in asymptotic safety. So it's a very preliminary work still, but you know, it's like a proof of concept, I would say, on how to approach this kind of ideas. And I'm not sure if you're familiar. This microphone is okay. Did you hear what I said?
Yes.
Oh, okay. So that was just a small remark. And so other than that, I wanted to ask you about the distance conjecture in both the bulk side and the CFT side, so to speak. So from the bulk side, regarding the what you call the distant axionics in conjecture. So on the one hand, the usual statements regard emergent strings. So the emphasis is put on the idea that the higher spin excitations belong to strings, one-dimensional objects. on the other hand, I seem to recall that in your particular papers, the emphasis was instead put on the codimension of the objects, which of course in 4 dimensions they coincide, but not necessarily in other dimensions. So, could you elaborate on this? And then I can ask the question maybe.
Yes, so whenever we talk about the leading tower, then it's typically, yeah, like particles or higher spin coming from strings, like dimension 1. And from the CFT perspective, what we see is like the leading tower as well. Now, it could be that you have other towers that become light at a slower rate, and they could correspond to excitations from wrapping branes and so on. Now, when we discuss this dimensionic string conjecture, that there is always some string becoming tensionless, indeed what matters there is the codimension, which means that if there is a generalization to high dimension, should correspond to codimension 2 objects, which means that it's not necessarily string, but it's not necessarily the leading tower either. So the idea is that it could be that the leading tower is a string or particles, but then there is always another tower, which is not necessarily leading, but that has a very important role in the distance conjecture, because might give an explanation for the distance conjecture in terms of this RG flow. And in that case, it's a tower of excitation modes, if you wish, of a codimension 2 object. Now, since it's not the leading one, you will never see the tower. It's just that there is an object with codimension 2 that becomes tensionless as well. Does this clarify the distinction?
Yeah, it's very clear now. Thank you very much. And from the CFT side instead, I know I did ask you this question before, but maybe since you you saw the talk by John South the other day, and you mentioned it here, I was wondering what your opinion was about generalizing outside of the context of conformal manifolds of exactly marginal directions, like using this generalized distance in the space of field theories to look at the distance conjecture from the CFT side, but without conformal manifolds, which also means perhaps without supersymmetry eventually.
Yeah, I think I really believe that there is a more general notion of distance that we should be able to define between different EFTs, like how far away is one EFT from another one, that somehow once we restrict to a modular space, like we connect vacua that can be connected continuously via flat modular space or a conformal marginal deformation, then it becomes the Samolnikov metric or becomes the field space metric. But I think this is just like a particular case. I really believe there is a more general notion that should correspond. I don't know if exactly what John is saying, but yeah, like some notion of how to define how far are 2 EFTs from each other. And maybe I like the idea that, for example, if you have a global symmetry in one of them and not in the other, then these theories should be infinitely far away from each other, because you can just, they are completely different, and probably that implies that you cannot connect them via some finite energy or some finite distance. So yeah, I think it's something that to explore, and I think that these conjectures should be generalized beyond marginal deformations, also to relevant or irrelevant deformations.
Yeah, exactly. Thank you very much.
All right, thank you. Check if there don't seem to be online questions. Just 1 second, let's make sure. I don't see it. Okay, please go ahead.
Hello, can you hear me, Irene?
Yes.
Yes, hello. Well, thanks very much for the talk. I had 3 questions, but let me choose just 2 of them. They are quick and to the point. When you explain the thing of the cobordism conjecture, right? So you explain that topological operators should not exist in situations like this. So basically, you always need to have an object where the say the Wilson line will end, right? Very good. So suppose that I consider then young mills plus gravity. In there, one would say any Wilson line will have nowhere to end, right? Cannot be broken. There are no particles transforming under the center. So that what this would be saying is that theory cannot be properly UV completed. Is that the way of thinking?
No. So when you have a non-abelian gauge group, it's true that you are going to have a one-form global symmetry that lives in the center, that lives in the center of the group, because the other ones are they can automatically end because of the gluons, no? Like all the right. Now you have to break. I mean, if you want to UV complete this theory, you have to break it or gauge it, and you can, and it's possible to do that if you have a complete charge spectrum, because then also the center, the one-form symmetry associated to the center will be broken. I mean, the operators will not be topological. So that's the correlation then to have I mean, it's not enough just to have some charge state. You need to have a complete spectrum so that the full center is broken. And if we have disconnected groups, it's even more complicated, because then, yeah, it's not just about the center. You have to check what are the possible non-invertible symmetries and so on. But in the end, everything, the conclusion is that you need to have some complete charge spectrum under the gauge theory if you want to
couple to gravity consistent.
Yeah, to get rid of any symmetry and couple to gravity.
Good. In the other part where you discuss the infinite distance in the Samolotchikov space, say calculated with the Samolotchikov metric, you made the point that whenever the theory is free, then you can indeed calculate this thing and see that these objects are infinite distant. Suppose that the CFT is at strong coupling, right? So what can you say in that case? How could we know if all states will be infinitely far away?
Yeah, so the thing, so part of our expectation is that the only way to go to infinite distance, to have an infinite distance point, is to have a free point, to have a weak coupling point. So the expectation is that if it's strongly coupled, then it's not going to be at infinite distance. It's going to be finite distance. So you are not going to have a tower of higher spin operators or tower of states becoming light. Now, there are several, I mean, in addition to the fact that it's motivated by all the examples we know of, there are more general like intuitions. In the sense, for example, from a CFT perspective, you could say that it's only when conformal perturbation theory breaks down, like as happens in the weak coupling point, that you can really generate the infinite distance. And since there is this one-to-one correspondence, because of Maldacena-Sigüedo between free point and higher spin tower, we know that if we have a higher spin tower, it is necessarily going to be a free point.
Okay.
That's a bit the intuition. But this is, I mean, whether this is the only way to go to infinite distance is what is not completely proven. They are just arguments and it's based on examples. And would be nice to prove it exactly in the CFT.
Thanks very much, Irene.
All right. Seems like no more questions. So thanks a lot, Irene.
Thank you. Thank you for the invitation.
And we'll close this section.